Hi guys, here's section 5.3, day 3 notes. We're still graphing polynomial functions. I have to show you guys a couple of things that can happen when you get a certain type of x-intercept or a certain type of root or answer to a problem. You haven't seen it yet on any of the other examples, so I need you guys to be aware of this. All right, when we are graphing polynomial functions, these are the steps that we follow. First, we find the x-intercepts by setting the equation equal to 0. We factor it if it's not factored for us, and then we set each factor equal to 0 and solve. Okay. Once we find the important x-intercepts, we plot the x-intercepts or zeros on the x-axis. Now what happens is you have to watch out for double roots or triple roots. You haven't seen this. What these are is what happens when you set factors equal to 0 and you get the same answer twice, like x equals 4 or x equals 4. So that's called a double root when the same answer happens twice. What if you get the same answer 3 times, like x equals 4, x equals 4, x equals 4? That's called a triple root. Well, something happens on the graph when you get these answers or roots or x-intercepts that have been repeated a certain number of times. So we have to go over what happens on the graph. All right, identify the degree of the polynomial, and find the sign of the leading coefficient. We determine the end behavior based off of the degree and the leading coefficient. Then we sketch the graph by connecting the dots and creating a smooth, continuous curve that has the correct end behavior. But we have to watch out for double roots, triple roots, etc. All right, I have a little note for you. This will just be a sketch of the polynomial's graph. Remember, they're just sketches, so my graph and your graph can look a little bit different, but there are certain points that should look exactly the same. All right, a more exact graph can always be found by making a table of values and created more exact points for you to connect. All right, but the easiest way and the quickest way is to kind of use your x-intercepts, the end behavior, and use that sketch. All right, so what do I mean by double roots and triple roots? Double roots, when an equation has a double root, the graph is going to what I call bounce at that x-intercept. It means it's not going to cross over the x-axis. So double roots are roots that were repeated 2 times, but really this rule applies to any root that was repeated an even number of times. So if you had a double root, or an answer that was repeated 4 times, or an answer that was repeated 6 times, or an answer that was repeated 8 times. Those are roots that were repeated an even number of times. So at those kinds of x-intercepts, the graph is going to bounce, which means it does not cross over the x-axis. Some math books will call this a root with even, and they'll use the word multiplicity. If you have even multiplicity, that means you were repeated an even number of times and your graph is going to bounce at that x-intercept. All right, well, if you are a triple root, an answer or 0 or root that was repeated 3 times, then the graph, it's called sits. I call it sits. It has this little bit of a flattening out effect on the graph, but the important part is that it does cross over the x-axis. So we'll kind of treat those ones like normal because there's still going to be a cross over the x-axis happening at that x-intercept. So again, a triple root is an answer that was repeated 3 times, but this really applies to any answer that was repeated an odd number of times. So if the answer was repeated 3 times, or 5 times, or 7 times, or 9 times, or 11 times, even 1 time, it's gonna cross over the x-axis, okay? So again, some math books will call that a root with odd multiplicity, which just means that that root or x-intercept was repeated an odd number of times. The important thing is to remember this: even equals bounce, and odd equals cross. But remember, when I talk about even or odd, I'm not talking about the degree. I'm talking about the number of times the root repeated. If it repeated an even number of times, the graph will bounce at that x-intercept. If the root repeated an odd number of times, it will cross over the x-axis at that x-intercept. All right, so let's try and give this a go with an example. Okay, so sketch each polynomial function graph. So here we go. We have to first, to sketch this, set it equal to 0 and find his x-intercepts. Well, lucky for us, it's already in factored form. So look, we have one factor of x, we have one factor of x plus 3, but this factor of x minus 4 is squared. So that means that you really have two factors of x minus 4. So I like to write it out. I like to expand it. This is really x minus 4 times x minus 4, because that's how many factors of x minus 4 you have when that factor is squared. All right, so now let's set each factor equal to 0. So if I set this factor equal to 0, x equals 0. That's one of my x-intercepts. All right, if I set this factor equal to 0, x plus 3 equals 0, x will equal negative 3. That's one of my roots or x-intercepts. If I set this factor equal to 0, I get x equals 4. If I set x minus 4 equal to 0 again, I get x equals 4. So I get a x-intercept at x equals 4 two times. That's what we call a double root. That's a root with even multiplicity, okay? So I like to circle those two and remind myself that's a DR, that's a double root, and the graph is going to bounce at double roots or roots with even multiplicity. So I put a little note. All right, now let's mark our x-intercepts. All right, so we have an x-intercept at 0, we have an x-intercept at negative 3, and we have an x-intercept at 4, but he is repeated two times. So I put a little circle around him to remind myself that something special is going to happen when we get to that x-intercept. Okay, now let's determine the end behavior. Well, because this was in factored form, I have to multiply all my fronts together to figure out the degree and the sign of the leading coefficient. So 1x times x is x squared. X times that x right there is x to the third, and then x to the third times that x right there is x to the fourth. So this would have led with a 1x to the fourth, which means the degree is 4, which means it's even. The leading coefficient would have been positive 1, which means what is the end behavior for an even degree polynomials graph with a positive leading coefficient? Well, remember, if you're even degree, your end behavior has to be both up or both down. If the leading coefficient was positive, which one is it? Both up or both down? It's both up. So to the left of my last x-intercept, put a mark. You know the graph has to end up. To the right of your last x-intercept, put a mark. You know the graph has to end up. All right, so now let's begin to fill in our graph. So I know it has to end up here, so I'm going to end up and head towards my first x-intercept. Now, any x-intercept that had odd multiplicity, so repeated 1 time or 3 times or 5 times, the graph is going to cross over the x-axis. These were normal x-intercepts. They were only repeated once. He was a root 1 time and he was a root 1 time. So at 0 and negative 3, your graph should be crossing over the x-axis like normal. So we cross over. What's my graph eventually going to have to do, though, to get to the next x-intercept? Turn. What's it going to do at the next x-intercept, which is completely normal? At 0, it was a completely normal x-intercept, so we cross over. So now what's the graph going to eventually have to do to get to the next x-intercept? It's going to have to turn again. But now this time, when it gets to this x-intercept was repeated 2 times, which makes him an even root, a root with even multiplicity, a double root. So what happens is the graph does not cross over the x-axis at a root that was repeated an even number of times. What it does is bounce. It will hit the x-axis at that x-intercept and then bounce right back in the direction from which it came. It will not cross over onto the other side. It literally hits that x-intercept and bounces right back off of it, and it goes right back in the direction from which it came. And this is how I can get my graph to end both up. All right, so again, it can be a little weird at first, but let's keep practicing. All right, let's try this one. If I want to graph this polynomial function, well, first I have to set them equal to 0. and I have to find his x-intercepts. This one is not factored for us, so we're gonna have to factor it. So the very first thing we should do is look for a GCF. What does an x to the fourth and a 2x to the third have in common? An x to the third. So take out an x to the third, and then what would be left? An x minus 2. Set that equal to 0. And now this is what we're solving. So now we have to set each factor equal to 0. Well, really, x to the third is really x times itself 3 times. So in reality, you have 3 factors of x. This is really x times x times x. That's x to the third. And then you're timesing that by x minus 2. All right, so now let's set all of our factors equal to 0 and get all of our x-intercepts, all of our zeros, our roots. So if I set this x equal to 0, I get x equals 0. If I set this x equal to 0, I get x equals 0. If I set that x equal to 0, I get x equals 0. So really, x equals 0 is a root that was repeated 3 times. So that's a triple root or a root with odd multiplicity. Okay, so that means the graph could do something a little bit different at him. All right, and then we set x minus 2 equal to 0, and we get x equals 2. So those are my 1, 2, 3, 4 x-intercepts to my degree 4 polynomial. It's just he's the same one 3 times. All right, so let's mark them on our graph. All right, so I have an x-intercept at 0, but really he was an x-intercept 3 times. So I put a little circle around him to remind myself that he's special. And then I have an x-intercept at 2. And he was only repeated 1 time like normal, so he's a completely normal x-intercept, and the graph will just cross over the x-axis like normal. All right, let's do our end behavior. Well, I can tell right now by looking at the original polynomial that this was a degree 4 and a leading coefficient that was positive 1. So if it's degree 4, that means it's an even degree polynomial. What's the end behavior for an even degree graph going to be? Both up or both down? Well, if the leading coefficient is positive, which one is it? Both down. So I know my graph has to end down to the left of my last x-intercept, and it's got to end down to the right of my last x-intercept. Okay, well, the good news is when it's a triple root or a root with odd multiplicity and a root that was repeated 3 times, the graph still crosses over the x-axis. It's supposed to have a little bit of a flattening out effect as it crosses over, the higher the repeated. So if it was repeated 3 times compared to 5 times compared to 7 times, each time it's repeated more, it gets a little bit flatter as it crosses over. But I'm not worried about that. So we're just going to make sure that we cross over. So I'm going to end down, and I'm going to head towards my first x-intercept. Like I said, in reality, the graph is supposed to kind of flatten out as it crosses over, but it doesn't matter to me. As long as you cross over, we're good. So I kind of flatten out and cross over. But what's my graph going to have to do to get to the next x-intercept? It's going to have to turn. So I turn, and then that was a completely normal root. It was only repeated 1 time, so that's just a normal cross. And then I don't have any more x-intercepts to head towards, so my graph just stays down. So again, to me, the double roots, the ones that repeat an even number of times, are harder because the graph will bounce and not cross. But if it's repeated an odd number of times, the graph still crosses the x-axis. So it really shouldn't feel like anything different happened with those ones. It's the double roots or the roots that repeat an even number of times that we have to watch out for. All right, let's try it again. All right, so let's graph this one. So if I want to graph this polynomial, well, again, I can already notice it's a degree 3 with a leading coefficient that is negative. So I already can kind of think about what his end behavior is going to be. All right, so let's set it equal to 0. It's not factored, so we're going to have to factor it. So I have a GCF of x, and I'm going to pull out a negative x to make, because it leads with a negative. That's going to leave me with x squared minus 6x and then plus 9. Set it equal to 0. And we're still factoring. I'm going to look to factor this again. So negative x times, well, if I factor this now, it's not the difference of 2 squares. I shouldn't need to group that. I know this piece and this piece get me x squared, so I need an x and an x. I know this number and this number have to multiply to 9, and then my rainbows better get me my negative 6x's. So I think a minus 3 and a minus 3 should work. Okay, now you can set your factors equal to 0 and solve. So if I set this factor equal to 0, set negative x equal to 0, divide by negative 1, and I get x equals 0. So 0 is one of my roots or x-intercepts. If I set this factor equal to 0, I get x equals 3. So x equals 3 is one of my roots, one of my x-intercepts, one of my zeros. If I set this one equal to 0,